Hey students, let's look at the second half of the test here, the free response questions here. All right, I'll start with, of course, I guess I'll call it 1, 2, and 3. It's in question number 11. And it is, again, a projectile motion. And a little bit harder than the 2 or 3 we saw on the multiple choice questions. Because, well, let's just read it here. An arrow is shot from the top of a bluff to a target below. And so it kind of angles, kind of like I've drawn here in the picture, and hits the target. The target is 35 meters below, and is below the launch point of the arrow, and the arrow is launched upward. And so there is an initial angle here of 55 degrees. With a speed of 35 meters per second, how far horizontally is the target from the launch point? All right, well, maybe I'll get a yellow piece of paper here, and I'll put page 1. I don't know if it'll take more than one page, but it might. Some of these can be kind of lengthy here. Maybe I'll draw a picture. So it starts here, kind of arcs up, lands 35 meters further down. And so let's put our grid or origin right here at the launch point. And I'll say the same thing as I've said in many of them. It doesn't require anywhere special to put your origin. It's kind of your choice. There's pros and cons of each of them. But most of the time, we put it at the launch point. So I'll do that. Then, if I kind of split my paper into 2, as you've heard me and watched me do many times, is let's calculate the motion of the arrow in the X as well as the Y. And so the second kinematic equation looks something along these lines. I'll just give the general one. It is conditional on there being constant acceleration. And we do have that. We have an acceleration in the Y direction only. So I'll write out the general equation of position for both X and Y, and then be a little more specific here. In particular, they're asking for how far horizontally does it go. And so they're after the X. So if I start maybe in this column, I'd say X equals, and this would be the pro of putting the origin there. It says 0. And of course, as we saw in, where was it here? The multiple choice questions. I guess it was back here on number 5. We talked about how, you take the velocity and then you get this angle, and then using the cosine function, you would get just how much of that arrowhead is horizontal, and then the sine function over here would give you how much is vertical. And that's why back here we put a sine and a cosine. And following that same logic here, we would say the initial speed is 35. We would then multiply by cosine of 55 degrees multiplied by t, and then I'll just, for completeness, put a 0 because there would be no acceleration in the X direction. Now, of course, by itself, we can't complete it because we don't know time, but let me just fill in what we do have here. And so I would go 35 times cosine of 55, hit enter, and then this becomes 20.08 multiplied by t. So that's about as far as we can go with the x-axis. Let's jump over here to the y-axis. And again, here's kind of the advantage or even disadvantage of putting the origin here. The advantage is the initial position is 0, which means we got to know how far down it goes, which does say 35 somewhere. Yeah, 35 below. So it's going to land at negative 35. So we need to make sure we interpret our math correctly. Below meaning down, and traditionally and I guess I didn't really say it, but I was calling the to the right a positive x and up a positive y. So that means down is a negative. Which is also why then the initial velocity will be positive, because the initial velocity is up, and it would be this 35 and then multiplied by sine of 55 times t. And then if you'll let me put the negative 1/2, because the acceleration is down, that's where the negative comes from, and it's 9.8, and half of that is 4.9, and that's a number we've seen a lot. In fact, we saw it again back on the, I think there were 3 multiple choice that had it. It was this number 5 we were just looking at it. See, there's the minus the 4.9, but in the easier one that it was shot horizontally, there again the minus the 4.9, and then back here, the one that even just went straight up had again the minus 4.9, and those were the other ones. Anyways, we kind of have that same thing. But now that you've written out the 2 equations, you can kind of see the big picture here on how to solve this crazy thing, because you can see here that there's only one unknown, which is time. So we'll solve this for time. And then once we get it, we can put it into here and get our x. So there's the strategy, if you will. Maybe I'll set it up like a math problem where we like to put all of the terms together. So I'm going to move this to the left-hand side, making it a positive 4.9 t squared. This number here, let me calculate that. That would be 35 times the sine of 55. And so that would be 28 point, I'll carry an extra one, 67. So 28, what'd I say? 67, okay, t. And when I move it over here from the right to the left, I meant to say that, from the right to the left, that would be a negative. And now the 35 is already over here on the left, equals 0. And then we have the quadratic solution. Again, like we did in the multiple choice. Did we do it more than once? Maybe not. Maybe it was just... actually, we didn't have to do the quadratic for this one. This one was factorable. Oh, it was way back in the 1 dimension, number 3 here. So it was pretty straightforward because it was 1 dimension, but it did have a little math in it that had a quadratic equation. So we had to write out the minus b plus or minus square root of b squared for ac over 2a. And so let's do that again. And so the opposite of b here would be a plus 28.67 plus or minus square root, and then 28.67 squared, so these b squared, minus a 4 times the a, which is the 4.9, and the c is a negative 35, and if you let me just put the 35 with the negative combining with that negative that's part of the quadratic formula, which is part of completing the square, that will become a positive all over 2 times a, and if you'll just let me put the 2 with the 4.9 to make an even 9.8 downstairs. And of course, like all these, let's do the square root stuff first here. So this is 28.67 squared plus 4 times 4.9 times 35, and then the square root of all that. Okay, and so this square root thing is 38.83. Now remember, we do have a plus or minus, and so like we did on the multiple choice, I think it was back in the 1-dimensional one, yeah, and this one here, where we solved this and we had the plus or minus, the question said on the way up. And so as we studied the mathematics of 2 answers, it made sense that there were 2 times that the ball was at 27 meters high, and we wanted on the way up. So we wanted the smaller of the 2, so we took the negative sign. Let's kind of apply that same logic here. This right here would be the equation of its position, and we're trying to solve when is it down here at negative 35? Now, if all you do is draw this much of the motion, you say, well, it only crossed at negative 35 one time and then continued on. But you could extend this by saying, well, these equations are equations that are really implying always having an acceleration of 9.8. And so, although it didn't really happen this way, the full parabolic motion would be in negative time in order to get here at 0, then positive time. Of course, in our case, it would hit the target and stop, but if time continued, it would, go even lower. And so technically, these equations are solving for moments of time that are before 0 and even after the hit target. So again, doesn't surprise that there is a moment in time. It would be negative of time. It'd be before it, got there, because we're calling this time equal to 0. So this, everything over here would be on its way to get to the launch point. And then this would be, this negative 35. So one of these answers should be negative, and the other one should be positive. And of course, we would want the positive one. So clearly the one with the negative sign must be the negative. In fact, you can even see that I did the square root at 38.83. So if I took the 28.67 and subtracted 38, I'd get a negative number there. It'd be negative around 10-ish, and divided by 10-ish would be around 1. So one of the answers is about negative 1 second, and that kind of makes sense. It would be here at negative 1 second, but it's not the one we're interested in. So let me just do the plus one. So now that I have the square root, let me just take the positive of it and add to it the 28.67. And then divide by the 9.8. And I get a time of about 6.89 seconds. And now using that to figure out the horizontal distance, I will take the 20.08 and multiply it by that last answer and get about 138 meters. And so there's the answer to our first free response question. How far did it go in the x direction? All right, great. Let's go on to the second free response. And I personally think the hardest one on the exam, although there is some cleverness we could do if you have gained some experience doing these. It kind of depends on, I guess, how much time really you spend on the homework. Because if you, well, I'll just kind of go through this. But if you recall, and I'll just kind of review here, and even though this problem has a double incline, if you put a block on here, and that's it, all by itself, you could do something like this. You could say, okay, well, here's the weight, mg, and then there would be then a normal force pushing back on it. And if there's friction, it would be opposite to the way it's moving. And I'll call that the normal force. In fact, I hope all of this looks a lot like question 9, where we said then if you kind of tilt your axis here, so that down the hill is x, and perpendicular to the hill is y. There is, of course, pros and cons to that. The pro is that the normal force is only in the y direction and nothing in the x direction, and the frictional force is only in the x direction and not in the y direction. That's really nice. Also, a bigger pro is that when it moves, and in our number 9, it didn't move, so that wasn't as big an advantage as this one's going to be. It moves only in the x direction, and therefore you have an acceleration of x, and that's all you have, and the acceleration in y is 0. So those are the three big pros of turning our axis. There is one con, and the con is, and I'll just kind of, let me go to green color, the force of gravity is no longer along your axis. Now, the force of gravity is still down. I mean, just because we tilt our axis doesn't change the direction of gravity. So when we tilt our axis, we still have this force of gravity down. But what we said here in number 9 is that this incline angle would be the same here. And so the force down the hill would be mg sine theta, and the force into the hill would be mg cosine theta. And I don't know, maybe I shouldn't have done the green. I don't know how well that stands out on yellow paper. That might be kind of hard to read. So looks like it's pretty good on my screen. I'll leave it then, but I'll stay away from the green here. So my point is, let's do the kind of the same logic, a little harder than what we did in number 9. Harder because now it's going to move and we have friction, and also harder because we have 2 of them. But like I said, that's why I think this is going to be the hardest one here. But keep this strategy in mind, because here's what I'm going to do. Let's come back to the picture here and let's label it. It says the block of capital M is 17. So let me put a 17 kilograms here. And the block of little m is 9.25 kilograms. Okay, so there's the mass of them. Theta 1 is 40 degrees. Let me put that in my picture. And theta 2 is 55 degrees. Let me also put that in my picture. Now, the coefficient of friction is 0.135 for both blocks. So the problem is pretty hard, which is why I go, you know what, I'm going to put the same coefficient of friction for both blocks. It'll be one easy thing among many hard things here. Which is why partial credit's, I think, crucial for this problem. What is the acceleration of each block? And I do help you out by saying they are the same. And so what's going to happen is they're going to move together. We really don't know if it's going to go towards the left, so this one goes down while this one goes up, or this one or goes towards the right, I'll call it, as this one goes down and this one goes up. So I'm really not sure which way they're going to move, at least not yet. So one of the hard things is really kind of figuring out, what direction it's going to move. And I think to do that, if you kind of look at this picture, what's pulling it down is its component of gravity. So if I kind of did this, then I said, okay, let's look at this block. What's pulling it down the slope to the left, and left down, would be this mg sine theta, where m is the mass of this block and theta is this angle. So this one should be the 17 times 9.8 times the sine of 40 degrees. And if we put that into our calculator, 17 times 9.8 times the sine of 40 degrees, we get 107.1 newtons. So that's what's tugging it this way. And if it actually moves that way, then the force of friction would be the other way. But the other block is tugging it in the other direction. Now, you might argue, don't they have a little rope connecting them? And they do. And here's how you can save yourself a little time on this problem, is that if I kind of think about this as one object, this is pulling with a tension T, and this one is pulling with a tension T also, but in the other direction. And so when I look at the forces on the two collectively as one big unit, the tension goes away. And that might actually be to our advantage. We don't actually have to solve for tension. Although we could. And it might be a couple extra mathematical steps because it's one extra unknown. But I'm going to take advantage of that because then I'm going to look at what's tugging it down this way. And the same logic. This is going to be an mg cosine theta. Now, really, this is theta 2. I probably should have put, capital M over here. So this would be the smaller m, the 9.25, the 9.8. But it is a bigger angle. And so mathematically, it is possible, but not likely, that this one's bigger. But given how much lower the mass is and the angle's not too much more, I don't think so. I would be surprised if it was. See, it's only 74.26. So here is 74.26 newtons. And here's what I'm trying to get at. What I would do first is just kind of really figure out in my head which way this is going to move. And since this tug at 107 is greater than this one, I know there's tensions, but again, those two balance each other. And there would be some friction also. So I can't do this problem completely without friction. And right now, I haven't included the friction. But I do know this. If it went down and to the left, which I think it would, then there would be a friction pulling it this way and a friction opposing the motion, so it would be going that way. So as this block goes up, I would have a friction, call it friction number 2, and I would have a friction over here of number 1. Okay. But that's what I'm getting at here in this quote-unquote free body diagram. And I would say I haven't even really got to the free body diagram because, again, what I'm just trying to do first is which way does it go? And I think now you can begin to see that it's going to go whichever of these two forces are bigger. We don't need to worry about the tension. We don't need to worry about the friction. If this one had bigger, we would say it goes down and to the right, and then we would reverse the directions of the friction, because the friction will always be opposite to the direction it's moving, but never would the friction contribute to the direction it moves. That's really what I'm trying to say. I should have said that at the beginning. The friction I can kind of ignore for a second to figure out which way it's going to move. And fortunately, we know it's going to move. There's another issue of, is there enough force to overcome static friction? And we fortunately don't have to address that one. That would be a question I would throw at my engineering class and say, well, does it even move? But since the problem says, what is the acceleration? We can safely assume that it is going to move. And now we just got to find out what the acceleration is. So I'll say it again, not an easy step, but that first big step is just what way does it move? And so I'm going to conclude, and I hope that made sense to you, that I don't need to worry about the tensions to figure out which way it goes. I don't even need to worry about what direction the frictional force is to figure out which way it goes. I just need to figure out which one has a bigger pull from gravity. The heavier one at a lower slope, or the lighter one at a bigger slope. And as we just said, the heavier one at a smaller slope gives me a downward tug of 107. The lighter one at a steeper slope is still under this one at 74. So it's definitely going to go to the left. Okay, so like I said, that can be a bit tricky in itself. You might even kind of guess it. I'm not going to make a big deal over how you exactly prove which way it goes. To be honest, I think most people would probably guess to the left because they would see the 17 and the 9 and go, wow, that's going to go that way. And maybe even overlook the different angles. But if not, they still would go, well, they're close to the same angle, not so much heavier. It's going to go that way. And then work from there. Okay, so let me work from there. And here's how I might make it a little easier in my mind. What if I did this? What if I just thought of the x-axis, if this makes any sense, as kind of arcing around over the top. It might be like saying, what if I just took this and just kind of straightened it out? You can see the force of gravity would be tugging it this way at 107.1 newtons. The tension would be pulling it back, and the force of friction number 1 would be pulling it back. And the other object would be connected to it, and so the tension would be pulling it in the direction it's moving, and the force of gravity down the hill, the 74.26, is this one, and then there would be also friction number 2. And if you then think of it then as a straight line, we actually have a much easier problem. This becomes kind of a one-dimensional problem instead of a two-dimensional problem. And also, if you think of this as, one big object, when you say, let's add up all the forces in the x direction and set it equal to mass times acceleration, you get something that looks like this, where you have the 107.1 pulling to the left. And I know that's not traditional to call that positive, but let me go ahead and do that just so that the direction it moves is positive. Because then on here, I would have minus friction 1, I would have minus tension. But notice this, on this block, again, thinking of all the forces on this collective system of 2, I would get a positive tension. I would get the negative 74.26, and I would get negative friction number 2, and that has to equal mass, and I'll put total, because I'm thinking of it as one big object times A. And that is why this is a pretty hard problem, right there. But notice then, like we did when we were just trying to figure out what direction it moves, thinking of the two collectively is really kind of an advanced thinking. They cancel off. That is really nice. Now, if you didn't do that, you could think of them as separate objects, and you would have these 3 equaling to an MA, and you would have these 3 equaling to an MA, and you would have then 2 equations. Each would have a tension, and you would solve one for tension and put it into the other, and then you would get this. So it's not much of an extra step if you don't put them together. But in fact, maybe I shouldn't have put it together. Well, no, I like that I put it together, and then I'll just say, try that. Because if you look at just the list by itself, you would have these 3, and then you would set it equal to MA. And then you would have these 3 for the next equation, set equal to MA. And then you would add them, and your minus T and your plus T would cancel off. Excuse me. And then on the other side, your masses would add together give you your day, and you would end up with this equation. So I think that it kind of makes sense of how it would work out. All right, now, before we can finish this problem, we probably need to take a moment. So it's a pretty long problem here, so let me call this page 1, page 2. Let's figure out the friction from number 1. And the friction is the coefficient of friction times the normal. And let me repeat it again. As we worked out here, the normal, the component is mg cosine theta. And I guess that's why I kind of was reviewing back here. This is the amount that goes into the incline, and the normal force balances it. And so I would have, for force number 1, let's see, the coefficient was 0.135, and the normal force would be mg, so that would be 17 times 9.8 times cosine of 40 degrees. And I'll get my calculator in a second, but force number 2, or friction number 2, would be that same logic. We have the same coefficient. It is a different mass. It's the 9.25 times 9.8. And it is sitting on a different incline of 55 degrees. So we don't want to overlook that. But both of those will give me a nice way of getting these two frictional forces, and then I can just solve for A when I'm done here. All right, so this one here would be 0.135 times 17 times 9.8 times cosine of 40. And so this is going to be a 17.23 newtons. And the other one's going to be 0.135 times 9.25 times 9.8 times cosine of 55. And that's going to be a 7.02 newtons. Let me just check. Did I put the right angle on that? Yeah, cosine 40. Okay, good. All right, so now let me bring this equation back here. So, all right, so pulling it down the hill, the mg sine theta for capital M is the 107, minus the friction here at 17.23, minus the force of gravity of the one that we're going to be pulling up the hill, and then minus also its friction. That has to equal then, and so it'll be equal here the total mass. What will that be? 17 plus 9.25 times A. So what's that? A 26.25 A here. And then this here is the 107.1 minus 17.23 minus 74.26 minus 7.02. And so we're looking at a net force of 8.59. All right, so if we take that and divide it by our 26.25, we get, is that really 26? Doesn't seem quite right. 7, 9, 16, yeah, okay. And so we get a 0.327. Yay, meters per second squared. And so there you go. And I would even add, if you got this one completely right, extra kudos for you. This is a hard one. Don't be depressed you missed it. I'm quite sure, though, you're going to get a lot of partial credit, because I have a feeling if you've studied the material, you'll have Newton's laws, you'll have the two objects, you'll have free body diagrams, and there'll be lots and lots of partial credit. But to get it completely right, you got to get all those pieces together. And like I said, kudos to you if you got that one. Now, number 3, the last one here, is a little bit of calculus one, and not a too hard a calculus one. So I don't think this one is as hard as these two, although because it has calculus, some people might argue, well, it's more advanced in its mathematics, but not too hard. Probably the biggest thing, though, is to make sure you don't put anything like V equals V naught plus AT. No. Or X equals X naught plus initial speed times time plus 1/2 AT squared. No. Or V squared equals V naught squared plus 2A X minus X naught. No. These are the ones, and this is kind of the big point of this problem, is to make sure you remember these are all great equations, and I only wrote down 3 and not all 5 of them, but if you know, those 5 I was showing you were only valid for constant acceleration, and that's what we've been doing the whole exam. And so far we haven't done any calculus, but our course requirement is that we have a little bit of calculus thrown into the mix. So let me throw in here a little bit of calculus. And so I guess I would start this way by saying something that acceleration is the derivative of the velocity, which means the reverse is true, that velocity is the integral of acceleration. And that's how we're going to solve this problem. Because the problem says here that we have a non-constant, and we have a varying acceleration. So if we put in the 1.24 t dt, and we integrate it, we get 1.24, we get t squared over 2 plus the constant of integration. And if we study this, we'll see that if you put in, so I'll say at t equals to 0 into this equation, you might call it v naught. You'd get a 0 here, and you'd get that constant. So that constant really represents the initial speed. And coming back to here, it says it's initially moving at 5. So this is a 5. So that makes our equation velocity equals, and if you let me cut this in half, let's see, 12 and a half is a 6, 2 t squared plus 5. So this would be our mathematical equation for the velocity as a function of time. And in this case, they say, what is the velocity at 10 seconds? So this would be 0.62, 10 squared plus 5. I guess 10 squared is 100, so that'd be a 62 plus a 5, making a 67. So there's the first part of it. And the second part is the continuation of that, because velocity is the derivative of position, which means the reciprocal is true, or the inverse is true, that position is the integral of velocity. So to get an equation for position, and I'll put page 1, I don't know if we'll quite go to a page 2. Let me do an integral of this equation, which is 0.62 t squared plus 5 dt. And when you integrate it, you get the 0.62, and when you integrate t squared, you get t cubed over 3. And when you integrate a 5, you get 5t, and then again, don't forget the constant of integration. In fact, maybe I should have put constant of my first integral 1, not to be confused with a different value, which is constant number 2. But doing the same logic, if you put in time equaling 0, you might call that initial position then. You'd get a 0, and you would just get then C2. And that was told to us. Its initial position is 17. So, okay, so this is a 17. So that makes our equation, x, equaling 0.62 over 3 times t cubed times 5t plus 17. And if we put that into our calculator, we're now done. So 0.62 divided by 3 times, and I'll just put in a 10 cubed, that's 1,000. 1,000. Plus, this would be 5 times 10, so that's 50, plus 17. So about a 273.7 meters would be the position. Nice. So not real hard, but definitely centered around calculus. All right. Hope all that helped. Take care. Bye now.